Okay, we are up and running. And the people in the room are also able to see this clearly. Excellent. So what we are going to do today is continue our conversation on Mips instruction set architecture, Mips ISA. Here, Mips is not million instructions per second. In fact, it is microprocessor without interlocking pipeline stages. So what is pipelining? What is a microprocessor? We'll look at all those things in detail as we go through the lectures. So this is just a quick recap of the things that we already learned, starting with the add instruction. So add instruction in Mips assembly language can be written in this form. You have add. The first thing is the destination, right? So this is a very easy way to sort of remember things. The first register that you see is your destination, followed by the other two destinations that are going to act as the sources, S2 and S3. So the add instruction is simply going to do this. It's going to take these two 32-bit signed numbers, add them up, and put the result in the destination, which is also a 32-bit register, in this case S1, which is identified by a number, right? So in the Mips reference sheet, hopefully everybody knows what a Mips reference sheet is. We are also calling it the green card, which is part of your textbook. It is also uploaded on the Piazza resources. Why do you need it? Well, think of it as three different stages: high-level language, assembly language, machine language, right? C, Mips, zeros and ones. C to Mips, the compiler does it, but on paper you are going to do it, right? So you are going to have to be a little bit creative about how do you translate a C code, say, to a Mips code. But we can do it if we have good understanding about the ISA itself. But from the assembly to the machine language, from the Mips assembly code to the bunch of zeros and ones, are you guys going to remember everything? No. You're going to need the reference sheet to make that conversion. So you're going to need it a lot of times. So have that handy. Next instruction that we looked at was the subtract instruction. After that, there were two instructions that had to do with the memory accesses. Load word, you're reading the memory. Store word, you're writing to memory. Now, whenever you talk about memory, you talk about an address. How are you specifying an address? You're specifying that by using two things. One, a base address, which is provided in a register, and an offset address, which is provided as a 16-bit immediate in the instruction itself. So you take a 16-bit immediate address, add it to one of the registers, which is functioning as the register in which there is a base address. Add those two, you get the target address. That is the address in memory that you can either read from or write to, depending on whether you are doing the load word or store word. So for example, if you are doing load word, you are bringing those things from the memory into destination. In this case is your S1, right? So from here to here, offset plus base address, whatever you find there, get it into S1. Store word, exactly the opposite. Whatever, what do you want to go where? You want things to go from S1 to a target address. Find the target address by adding the offset to whatever you have as a base address in S2. You guys see that? Questions about these four instructions? Mips, add, subtract, load word, store word. Which are, so if you had to classify, pick which ones are faster in this one. Good. Add, subtract are going to be much faster than load word and store word. Memory, the moment you look at memory, things are going to become 100 to 200 times slower. Okay. So let's talk about some good design rules, which are going to require some good compromises. Let's keep all the instructions the same length, 32. So what we have is an ISA, an instruction set architecture, which is byte addressable. So I can talk about the address of each byte. However, things are word aligned, right? One word after another word after another word. And over here, one word is 4 bytes, just so that everything is consistent with the number 32. 32-bit registers, right? Have different formats for different instructions. In fact, we are going to see 3 of them: R type, I type, and J type. Each type of instruction has a specific purpose. For example, R type are going to be register to register transfer operations. And then I type are going to have register, immediate type operation. And then J is your jump type operations. We're going to keep the format similar. And let us start looking at some examples here. So R type instructions, also called as the register to register operations. This is what? This is the instruction register, right? This is the instruction register that belongs to that type of instruction, R type instruction. Remember where the instruction register fits in to our instruction cycle. Starts with program counter. Once you load the program counter into MAR, perform a read cycle, things from the memory through the MBR get into the instruction register, right? That's your instruction fetch. Once they are in the instruction register, then you start decoding and working on that instruction. But instruction register is the register that we are using to hold the instruction to work on, right? It's not the address, it is the instruction that we are trying to work on. So earlier we talked about 2 fields, opcode and operand specifier. That was okay then. It's not okay anymore. Why? We are looking at it in a lot more detail, down to the bunch of zeros and ones. So what we have is not 2 fields. In fact, we have more than that, and it varies depending on the format. So for example, for R type instructions, what we have is 6 bits for opcode. You don't need to remember this. Where are you going to find this information? Mips reference sheet, right? So don't need to remember this. Everything is provided over there in a lot of detail. But we are going to need to understand what is the function of each of these fields. Opcode 6 bits, followed by 2 source registers. Why do we need 5 bits to talk about source registers? There are 32 source registers, so I'm going to need 5 bits to identify any one of them, right? So I've got 5 bits to talk about the source register number 1, source register number 2, and then I also have the destination. Remember, in R-type instructions, operands are in the registers, destination is also in the registers. Where are the registers? In the register file. What is the alternate? Memory, right? So you have register file over here where accesses are going to be much faster than to the memory. So as long as you are in the register file, things should be much faster compared to a load word instruction, for example. So you've got 5 bits for RS, RT, and then the destination. You find something weird over here. You remember when we were trying to write assembly, we were writing destination first. But when we write the field, destination actually last. So why do you think that is? Like we didn't have enough confusion or reasons for confusing people? The only reason for that is so that the instructions can have a similar format. So when you look at the I-type instruction, you will see that the I-type instruction will have opcode, will have RS, will have RT, but it will not have RD field. Instead, all of these will be combined for a 16-bit immediate field, right? So in order for having some consistency in the various types of formats, RD is placed a little bit at the end. However, when we were writing assembly, the destination was actually the first thing that we were talking about. You guys see what I'm saying? Yeah, all right. Next one is the shift amount. Where is this applicable? For shifting in instructions. Give me an example. Shift logical left. Why would you ever want to do shift logical left? Say I want to multiply things by 4. Going to be pretty useful, right? Why? Conversion of words to bytes. You are going to need that many times. So when you're trying to multiply by 4, you can simply shift left logical by 2 bits, right? So that field is for shift. By the name is shift amount, and you have 5 bits for that. Do you need 5 bits? Maybe not, but you're trying to occupy that 32-bit field so that all the instructions can be 32 bits. The last one is a function field, which is again 6 bits. What is the difference between opcode and the function field? Well, opcode identifies the operation. Function field identifies the variation of that operation. For example, we have add. We have add u, add unsigned. 2 different instructions having the same opcode, however, a different function code. So you reserve some of the last 6 bits of the instruction corresponds to the function field for variations of instructions. Where are all the instructions listed? On the MIPS reference sheet. And if you go there, you will be able to see their opcode, let's pull it up. Let's pull it up to see a couple of examples here. So if I go all the way down, I have this MIPS green card. I can bring this into my app. Sure. New document. Okay. Right. So the first instruction itself over here is say add, right? So I'm looking at this guy right here, add. You also have its operation. Register RS plus register RT goes into, the result goes into register RD. What is the opcode? 0. What is the function code? 20 in hex. So all of these entries are in hex. So you'll have to be a little bit careful because the entries in the machine language are going to be zeros and ones. So a quick conversion is required over there. How do you identify RS, RT, RD? Well, you'll have to look at the register numbers. If you are talking about S0, you would refer to it as register number 16. If you are talking about K0, you would refer to it as register number 26, and so on. Those are in binary, decimal, or hex. Of course, not binary. So are those numbers in decimal or in hex? The register numbers. Observe, so you have things from top to bottom. I only see zeros through nines. I don't see A, B, C, D, E, F. So it's got to be decimal, right? So 0 to 32, sorry, 0 to 31, all decimal. So opcode given in hex, function code given in hex, register numbers given on the sheet in decimal. Eventually, you are going to have to convert things to binary. For how many bits? Well, if it is an R-type instruction, 6 bits here, 5, 5, 5, 5, and 6. So starts and ends with 6. Everything in the middle is 5. And like I said, to keep things consistent with an I-type instruction, that's why we put RD all the way over there, right? So you have opcode same, RS same, RD, RT same. And then you have immediate, 16-bit immediate there, used either for a constant or for the offset address. Right, so it is used for different purposes. All right, let's, and there are a lot of other things. You will need to refer to this as you work through MIPS architecture. Go ahead.
It says, is the shift used as an offset?
Yes, so shift is for, not an offset. Not an offset. Shift is a field given in the instruction for shifting bits left or right. So that depends on whether your instruction involves a shift or not. If it doesn't involve any shift, then you don't need that field at all. You will fill it in with a bunch of zeros. I'm trying to think of, you see this over here? Here you have shift left logical and shift right logical operations. in which you are moving the contents in that register by those many bits, right? So 2, 3, 4, or you're just moving that by the shift amount bits. Those are the only two operations I think we need the shift amount, at least in terms of our integer operations. Right, those are the only two. So I hope that answers that question. Let's go back. We talked about all these things here. All right. Example of an R type. Oh, go ahead, Bennett.
Show the shift in the assembly code.
How do you show?
Yeah, like if you don't want, or if you do want shift, how do you put that in the assembly?
So you do that with the shift like this. Let me go back over here. You see this shift left logical. It is an R type instruction. So you're going to need to fill out all of these things, right? So you have RD, RT, there is no RS, so a bunch of zeros there, no RS. And then shift amount is going to be there. In terms of opcode, it's a 0. In terms of function code, it is 0, 0. Right.
It has something in RS, or it is import?
Yes. It is just going to pick out RT. So I guess the confusion is because only some instructions require a shift, almost all the others don't. But the idea is to group things into types of instructions, right? So that's why R-type instructions, this is the format, use this for all R-type instructions. When you're doing add, your shift amount doesn't play a role. But when you're doing a shift, that's when it plays a role. So, yeah, move on. Okay, example of an R-type instruction. This is assembly code. Add what to what and the results go where. S1 to S2 and destination first. Take 32-bit signed number in S1, add it to another 32-bit signed number in S2. Those are identified by registers numbers, 17 and 18 respectively. And then your result goes back into a temporary register, in this case T0. Remember, we are putting a prefix of $sign before every register name, right? Not for the number, but for the name. Now, if this is an R-type instruction, how am I going to need, what do I put where? Well, for opcode, I had 0. I looked at the Mips reference sheet just a bit ago. It was 0 for opcode for add, and it was, I remember, 20 for the function code. I wrote 32 over here. I don't know why. That was the function code for add. Why is there 32 here? Sorry? Decimal, right. So this is 32 in decimal. And you guys are all like experts at converting numbers to decimal to binary and all that, right? How would we do it? 20, would we use positional significance, or there is a better way to do it? What is that? Yeah, but then that might become a little bit tedious depending on the number, right? So I would do binary as the middle point, 0, 0, 1, 0, 0, 0, 0, 0. I know this guy is going to be 32. Yeah. So convert it to binary to make things easier for yourself for the conversion. All right, let's move on. For opcode, it was 0. Reference sheet. RS. What is RS? S1. Number 17. Binary 16 plus 1. Yeah. 18 for RT. S2. Just add a 1. Where is the result going? To T0. What is the number? 8. Believe me. T0. 8. Yeah. Come back. So that's your destination. 8 is easy, right? 0, 1, 0, 0, 0. What was the opcode? I think it was 6 bits of 0, right? All right, shift amount, no shift. Function code 32, 32 in decimal. 1, 0, 0, 0, 0, 0. That should be it. So what we have done is we have taken let's do complete. Let's do complete. So let's say what would be a C code for this? In C, it probably would be say A equals B plus C, right? Something like that. When you have in high level language A equals B plus C, you are representing A, B, C as registers. In this case, A is being represented by T0, destination. And then it doesn't really matter here, B, let's say this guy, and then C, let's say this guy. So C to MIPS down to zeros and ones. Zeros and ones, you can see all the 32 bits over here. Questions? So what is going to be important here? Is it particularly difficult? No, it's not. So what is important here? Being a little bit very like a detailed oriented person, right? Like somebody who's paying attention to small little details, they are going to do a pretty good job. Is there a way for you to check? I'm a fan of having multiple sources, right? So having multiple ways of checking whether I'm going in the right direction or not. So if I was doing this and my life depended on it, I would not just base things off of MIPS reference sheet and then just rely on, moving the zeros and ones to paper and the MIPS reference sheet. I would also use a simulator. And there are a lot of MIPS simulators out there that are for free. There is one that was designed and developed by Mississippi State called MARS, M-A-R-S, which is pretty good. Uses Java runtime environment to execute. You can have it on your Windows machines. You can have it on your MacBooks. Just go online, see Mars. How do you execute add statement? And it'll give you. You'll have to just simply do that, right? Create a new assembly language program. Write that instruction. Add this to this to this. And then depending on what these registers already contain by default, it is going to do that as an addition and it's going to put the result back into the T0 register. So it'll let you see the assembly code and the work the assembler does. So it'll also let you see how it translates the assembly code into a bunch of zeros and ones by the assembler, and then it'll also execute it. So it'll show you how the contents change. So I would have used that as well. And if you guys are finding it difficult to locate the simulator, it's not a required thing for you guys to do, but if you're interested, I'm pretty sure things are so simple for you to download and run and play around that you're not going to need any sort of additional help. But if you do, let me know and I can show you that interface. Let's see. Let's move on. I-type instruction, immediate type instruction. What are they? They are used for specifying non-register operands. Where are my operands? Well, it could be in my register, but some part of my operands are also in the specified in the instruction itself. Immediately. So why is this useful, I-type instruction? Well, for a bunch of instructions. Actually, the majority of our instructions are going to fall in the category of I-type instruction. Load, store word, load word, store word, branch when equal, branch when not equal. What else? Add I, or I, and I, all the immediate type of instructions. They're all going to fall in this category. So what does it have? It has the same opcode field as before. It has two register fields for RS and RT. Both of them are functioning as sources. These are sources for the operands. These are not sources, source versus destination for the instruction, right? So what that means is, let's see, in a store word, right? In store word, what is happening? In a store word instruction, one of the registers is the source and it is actually ending up in the memory, right? So that's where the source is the source. But what about the load word instruction? Your memory contents are coming into a register, but we are still calling that register a source here because it is the source for the instruction, right? Not for the result. You guys see the difference there? So it's not like A plus B equals C. The answer is going in C, so that's why we are calling it destination. Over here, depending on the context, the registers might be a source, might be a destination, but we are calling them both sources as far as where the operands are, or they could be. So RS and RT are your 5-bit identifiers for the two registers, and then followed by the 16-bit address or an immediate. It is a signed number there, 16-bit, provided as part of the instruction itself directly. So it could be used as an address, load word, store word, could be used as an immediate, add I, and I, or I. Let's take a look at an example here. This is our load word, byte addressable and word aligned architecture here. 100, the load word over here has S1, it has an offset as 100, and it has $S2. Does the offset over here need to be a multiple of 4? Does the offset over here need to be a multiple of 4? Load word and store word. Yes? Good. Yes. So that's right. But that's the answer for a different question. That's the answer for if a number is multiple, it's a multiple of 4, then what are the last 2 bits? That's the answer for that. But over here, the question is it the offset? We know that that is the offset, right? 100. And we are going to specify that is in the 16-bit immediate field. Question is, has it already been multiplied by 4, or do we need to multiply by 4? So let me sort of go back to the example that we looked at in the last class, just to refresh your memory about this guy right here. So you see over here, we said the offset was 32. We had multiplied it by 4 and provided that offset, which in other words, offset is in blank, bytes, words. It's already multiplied by 4. So if you're multiplying by 4, you get more, right? So you get more bytes. Yeah. So whenever you're writing a load word instruction or the store word instruction, the offset is represented in bytes, which means that you are going to have to multiply the words by 4 and put that as the offset in that 16-bit field. That's your offset address. Where is the base address? This guy has the base address. Next question. Base address in S2 is 32-bit. Offset, my offset address is 16-bit. So how should I do that addition? Because I'm going to need to do this addition, right? I need to do this addition. How can I add a 32-bit number to a 16-bit number? You put zeros at the front, right? So you have got, no. Can't do that, sorry. So here is the problem. Can't do zeros at the front. What if it's a negative number? So if it's a negative number, its most significant bit is going to be a 1. So we are going to need to do a sign extension for that, right? So if most significant bit is 1, then you will pad it with a bunch of 1s. If it's a 0, then you will pad it with a bunch of zeros, because that is going to be a signed number for offset. In other words, whenever you're doing that offset, if this is your base address, you can go below it and you can go above it, positive and negative. You guys are all with me with that? So it's going to be a 32-bit number is here and the 16-bit number is here. You're trying to add that, but what goes here could be a bunch of zeros or could be a bunch of ones, depending on whether the number is positive or negative, respectively. The offset was positive or negative. All right, so let's move forward here. So you look at this particular address, right? You've got the addition here. You've added these two guys. You've got the target address here. Oh, let me not do that. Let me do this. You've added it. You've got the target address. Go look at that memory location. You're going to find some word there. Bring that word, load word, not load byte, load word into the register. In this case, what? S1, right? So opcode 35. Who tells me that? Well, where is our load word instruction? LW. Right here, load word. 23 is your opcode. Is there a function code here? Nope. You only have the opcode field here. 23 to hex, convert it into decimal, you've got 35, and you can also represent that as what? But you know how to do that conversion. 2, 3 can easily be converted. Now, you see this? The meaning of that instruction. Base register plus the sign extended immediate, right? You see that? Sign extended immediate. That's why we said bunch of zeros or bunch of ones, depending on whether it's a positive number or negative number, which is called what? Sign extension. We don't formally learn about sign extension in COCO, but it's one of those things that I sometimes mention it and sometimes I don't. So you may or may not have heard sign extension from me when you are going through COCO, but that's exactly what we use it for, right? Sign extension. Pad it with zeros and ones. In other words, extend the sign so that the number of bits become consistent. Because -5 is the same as saying -5 or -05, -005, and so on. Let's see. So you've got 35 for the opcode in decimal. This is in decimal. I guess we can write out the 6 bits for this, right? 2 is this guy and 3 is this guy, right? So that's your 23. 18 is fine. Oh, no, is it? 16 plus 2, that's okay. 17 is this guy. 1 for RS, 1 for RT. Which one is RS? Source. S2, this guy, right? So take the source and that's your base address. Destination first, right? Add these two, put that over here. What is this? This is your destination register. Number 17, write the binary. And then the last one is the 100. How are you going to specify 100? As a signed number. So convert 100 into 16-bit number. So a bunch of zeros and then the last few will be corresponding to the value 100. Questions? So it's going to be slower than the other instruction, right? Because I'm going to have to do a read cycle for the memory. That's what makes it slow. You are providing the number in the instruction register as an immediate, fast. You are accessing the register file, still fast. You are accessing the memory, things are going to become slow. Next, add immediate, one of my favorite instructions because it's very useful, very simple. Add immediate. I'll immediately give you a constant, you just do an addition. And as the name suggests, add immediate. It is a I type instruction. So the 16-bit field over here, it is actually reserved for that immediate constant. Small constant or big constant? Well, it is going to be a 16-bit constant, right? So whenever you have a 16-bit signed field, it is going to give you a limitation, a range, right? Anybody remember what is the range of n-bit numbers from COCO for 2's complement? 2C range, n bits. So over here, your n is going to be 16, those many bits, right? So if you put it over there, you are going to get negative 2 raised to 15 to 2 raised to 15 minus 1. That is going to be your range to provide the immediate numbers. Okay, so let's try to see some examples here. Add immediate. The C statement over here is whatever there is in the variable B, add 100 to it and store the result in A. A, I'm going to use a register. B, I'm going to use a register. 100, well, I could use a register, or I can just give it into the instruction itself using the add I, right? Because if I use a register for that, I'm going to have to first initialize that register with 100 and then do this add instruction. Or I can just do an add I instruction. So let A reside in T0, right? A temporary register. Let B reside in T1. What if I chose S0 and S1? Would I be wrong? Absolutely not. So my choice of registers is one based on context, two generally my choice, right? I would stay away from stack pointer. I would stay away from the one reserved for the assembler. I would definitely stay away from the 0 register, right? I wouldn't mess with, you cannot change it anyway. But I would not use it to sort of change the contents. Saved registers and temporary registers, I can use them for the programming purposes. All right, so A in T0, B in T1. The assembly code for this, add immediate T0, T1, 100. Take T1, add 100 to it, destination is T0. Add I, opcode is 8, Mips reference sheet. RS, what is our RS? T1, right? Number is 9. RT, T0, number is 8. The immediate in this case, 100. Signed immediate. So that's going to take up that 16-bit field over there. Again, it is signed, so you can go plus or minus. So example over here is where you are using that immediate field to provide a constant. Earlier, we used the same field to provide a offset address. Questions? So far, so good. This is going simple. Where do I use add I the most? I use add I the most for initialization. For example, if you want to do any sort of C program, the first few steps after you import the appropriate libraries, the first few steps are what? Initialization. I equals 0. How do you make I equals 0? So suppose your C statement was this, right? I equals 0. And let us suppose for I, you're using some temp register, T3, right? So let's suppose we are using $T3 for this. How can I do this? In Mips, add I, destination is $T3. What is my source? What is that? 0 and 0, right? So the constant is 0. The source register is 0, fixed. I can't change that. and then my result goes in T3, which is sort of I. Go ahead.
T3, the default is 0, the default value in it is 0.
Right. So if I was writing a program, if I didn't initialize things, then the registers, whatever they had contained from earlier instructions, that's what is going to continue. But if I don't want that to happen, if I want to sort of dictate things from the beginning, make this 0 and then maybe accumulate or maybe do a differentiation or whatever that program demands, then I want to start it off at 0 or some, maybe a 1, maybe 100, I don't know, depending on the context, right? If I want to start it at a particular number, then I can use add I instruction to sort of initialize things. If I didn't do it, then I don't know what T3 holds. Right. Oh, no. So after this instruction, yes, we make it 0. But before this, there is no way for me to know what is in T3. Yeah. Yeah, after executing this instruction, it will be 0. Let's see. Let's go to the other few types of branch type instructions. When do you do branching? Well, this is useful for comparing things, right? If this equals this, then go to that address, which essentially means instead of updating the program counter one after the other, put this new address in the program counter so that it effectively is like jumping to that particular location in memory and start executing programs over there. So branch when equal, BEQ. BEQ, register 1, register 2, L1. What is register 1 and register 2? Those are the two registers whose contents you are comparing. And if they are equal, branch when equal. If they are equal, you will branch. Where? L1. What is L1? It is an address in the memory. Right? It's not an address in the memory. It is actually the offset using which you can compute the address in the memory. Because we only have 16 bits for this, right? We only have 16 bits using which we can inform our assembler about what L1 is. You guys see this? Register 1, register 2. Compare them. If they are equal, branch when equal. If they're equal, branch to L1. What is L1? It is an offset address that is used to compute the address to which program counter needs to be updated to, right? You guys do this in C, right? Like a go to statement. You guys have done that, right? Go to label. In C, you have done that? No? How do you do jumps in C? Look, it's been a while since I've written C programs, 2001 to be specific. I remember from then, go to followed by a label was a way my professors didn't like it because it involved a jump, but that was a way for us to jump around in the program. Go to is a statement, right? You haven't used it? Who is a C programmer in the room? Oh, wow, your professors are more strict than mine. All right, let's talk about the branch when not equal. So for branch when not equal, register 1 compared to register 2, if it is not equal, then you branch to L2, right? Question? So you have branch when equal, then you have branch when not equal. And I suppose by now you might think, yeah, I could have used this, I could have used that too, right? They're both sort of interchangeable. Turns out the compilers really like for you to use the branch when not equal, because things being not equal, you don't want to jump all the time, right? You don't want to compare for equality all the time. You compare for inequality, turns out to be more efficient. Even though they can be used interchangeably, BNE is a lot more efficient as far as the compiler is concerned. Let's talk about this. So the BEQ and BNE, they are again going to have certain opcodes. They are going to have the two registers, RS and RT, register 1 and register 2, and then it's going to have that relative address offset. Relative to what? Relative to the current program counter. So you can go away from the current program counter up or back in memory, which also means that that relative address offset is going to be a signed offset, plus or minus. Example of BNE over here. You have a very innocent looking C code, just an if statement, and you're comparing the contents of I and J, right? Value of I and J. If I equals J, then you want to execute this particular statement, H equals I plus J. And we are assuming that I is being sort of represented with a register S0, J is being represented with S1, H is being represented with S3. So what we want to do is, we want to do that comparison first, if I equals J, and if it is equal, then you do the addition. If it is not equal, then what? Then you do some other statements, right? Whatever follows in the program. So how are we writing this in Mips? We are doing it this way. Branch when not equal. Branch when not equal, what are you comparing? S0 to S1. What are S0 and S1? I and J, right? So this essentially means if I doesn't equal J, branch when not equal. If I doesn't equal J, then go to L1, right? Do you guys agree with that? If it doesn't equal, I doesn't equal J, then go to L1. What is L1? L1 is a memory address, memory location that points to the next instruction. After add, it could have been something else. That's where it is going. But what is going to happen if it is equal? If it is equal, it will do the addition, right? If it is equal, it will not branch. And if it doesn't branch, by default, program counter keeps updating to the next instruction. The instruction is 4 bytes away, so it's going to do PC equals PC plus 4. In this case, it's going to do that addition. So if it is not equal, if it is equal, it will not branch and execute the add instruction, which is going to correspond to what? H equals I plus J, right? So this is an example where you have your C code had a equality comparison, but your Mips assembly actually used a BNE statement. Questions here? Good. Oh, sorry, I'm not able to hear. Oh, very good question. So for that, so the question right now in the room is, how do you know what L1 is going to be, right? So I've given you the address of BNE, 100. What is L1? PC equals PC plus 4. We are talking in bytes. So I said 100. L1 is going to be what? 108. Right? So that's what you are going to talk about over there. Let's see. You don't even have to give 100 actually. You just need to give it plus 2, right? Because it's relative to the current program counter. So it's already all you have to do is in bytes you have to give it. Actually, this is branch. So you give, so there's a whole story behind this. For branch, the offset is in words, not in bytes. Because whenever you branch to a word. You don't branch to a middle of a word, right? So in branch, again, this is sort of next lecture. We are trying to pull things off. In the branch statement, the offset is in words. So you take the words, multiply by 4, and then you get the next one, right? So for this case, L1 would be just 2. But if it is load word or store word, the offset is in bytes. Let's see, other questions? Last type of instructions, J type, jump type. There are only 2 of them, jump register. So J and JR. And in this, it's probably the simplest instruction. Opcode field followed by a 26-bit address. Why is the jump instruction used for? To jump to a particular memory address. What does that mean, jump to a particular address? That essentially means whatever program counter you have, dump it, use this new program counter. So work on the program that is located at that particular address, right? No comparison, just jump. So at this point, you guys must be scratching your heads. He said 32 bits. And over here, there is 26 bits. How are we going to know the location of a memory address with 26 bits? That would be a very, very good question. And the answer to that is going to open up a lot of ideas for you. Can I say that in a word aligned format, word 1, word 2, word 3, the addresses are always a multiple of 4, right? If things are a multiple of 4, we know that the last 2 bits are 0, right? So when I know that the last 2 bits are 0, why use 2 bits for that? Why can't I just provide things apart from the last 2 bits, right? So that is going to be the first thing. Whatever you provide over here in this field, it's a 26-bit address, but because I know that the last 2 bits are going to be 0, it's a multiple of 4, that is going to give me 26 bits followed by 2 zeros. Still makes it 28 bits. Still need 4 more. Where am I going to get the 4 more from? From the current program counter. So wherever you encounter a jump instruction, that is going to have a certain program counter, right? It is going to be located at some particular address, some L1. That L1 is also going to be 32 bits, which means that it is going to have the most significant bits, 4 most significant bits, as the 4 most significant bits of the program counter. So you take the 28 from here, and then you get the remaining 4 bits from the current program counter, wherever you encounter that jump instruction, to make a 32-bit address. That's where you will jump to. So whenever you are jumping, you are sort of jumping relative to the program counter, but this jump is going to be pretty big. It's not going to be limiting as a branch instruction or branch when not equal instruction. Because over here, instead of 16, we are going full 26 bits. Questions here? The opcode for jump, I think it's 2, and for jump register is 3. That's what I remember it as. Let's just check. Jump, is it 2? Jump, 2 in hex. And then jump register, jump and link is 3. Jump register is 0 and 8. So jump and link instruction is used for storing sort of the return address. So we'll take a look at JAL, jump and link instruction, maybe in the next class, maybe after that. But jump is over here. 2 in hex is the opcode for that. if then else example, C to MIPS. And we all know how to do MIPS to machine now. What do we have over here? If I doesn't equal J, then do the addition. If it is equal, then do subtraction, right? Very simple. What are we doing? For every C line, we are writing an equivalent MIPS instruction. MIPS code for that. If I doesn't equal J, then do addition. How are we writing that? We are writing that as a branch when equal, and you are comparing S3, S4 to S5 and jump to L1. So before we go any further, we are going to need to associate registers with the variables being used, right? So I, J, and H. Can you guys help me figure that out? I is being denoted by which one? H is what? J is what? I is S4. Excellent. So there were multiple layers. So with this answer, there were two potentials, right? There were two places where you could have gone wrong. One place where the mistake would have been very easy to commit is the I and J swapping. You see this? Because addition is commutative, it doesn't matter which way you do it. You could have said S4 and S5 for I and J the other way as well. However, when you have a subtraction over here, you look at S4 for I, S5 for J. That will sort of box you with one choice. So I has to be S4, J has to be S5. H is easy. Destination over here, S3. Destination over here, S3. That's sort of pretty easy to figure out. So once we do that, now let's go do this. Branch when equal. What are we doing here? We are comparing the I and J. And if it is equal, you are jumping to L1. Where is L1? L1 is over here, right? In other words, if I and J are equal, do subtraction. Yeah? Good.
Wouldn't it be more efficient to do beginning and then swap?
Oh, yeah, absolutely. I think that's my next slide. No, that's not my next slide. But test for that's sort of right here. So testing for not equality is much more efficient. Over here, we are just giving an example of how to do it with equal. All right. So if you look at these two statements, branch when equal, and then this guy, looking at those two, you can say if I equals J, then we will do a subtraction. It is the same way as saying if I doesn't equal J, I'll do an addition. If not, I'll do subtraction. Right? So if I equals J, then I'm doing subtraction. But what if it is not equal? So branch when equal. What happens when you don't, when they are not equal? It doesn't branch. If it doesn't branch, PC will simply equal PC plus 4, as opposed to PC equals PC plus 4 plus branch address, right? So when it is not equal, it will simply execute the addition operation. After the addition operation, it has a jump instruction to L2, right? Because if we didn't have that jump, it would execute even the subtraction. So we do the add and then we do the jump. Questions here? You guys agree that this sort of matches this? But as Bennett pointed out, there are variations to this. We could have accomplished the same goal more efficiently with BNE, in which we could avoid the jump. Good. address of L1 is 112. So here, like I said, L1 is part of the branch instruction. Branch instruction, you provide the offset in signed words. So the number of words that you're jumping over is this, right? 1, 2, 3. So L1 is simply be plus 3 in this case. So hopefully that answers that. For load word load word, store word, things are in bytes. For branch, you never branch to something in the middle of a word. You always branch to the start of the word. So why provide information in bytes? We'll provide it in words. Word.
So would the address of the actual L1 instruction be 112 then? The subtraction instruction, would that be 112 because it was?
Right. So
Yeah.
the whole address is going to be whatever that 32-bit address is. But in the instruction, I'll just give 3.
Yeah.
All right, let's see. Let's talk about loop. How do we do loops? In order for talking about loops, we need to talk about inequalities. How are we doing that in Mips? This is a very useful instruction here. Set on less than. Set the contents of a register to 1 when this is less than this. So you're essentially comparing for inequality, right? So the example over here is if S1 is less than S2, if the contents of register S1 are less than S2, go to this particular address, L1. The way you can accomplish that in Mips is this. Set on less than, you are comparing two registers. In this case, you have S1 and S0. If S1 is less than S0, then you are setting T0 to 1. Otherwise, you are letting it be 0. You see that? Set on less than. If S1 is less than S2, then you are setting T0. To what? To 1. Set on less than. And once you either set T0 to 1 or not, you can execute this branch when not equal statement. What is that? Branch when not equal. What are you comparing? T0 and 0. If it was set to 1, it wouldn't compare and it would jump. Branch. When it is equal, if this is equal to this, then it will not branch, which means whatever instruction is over here, it will execute that. Next one. You guys see that? Set on less than. So this instruction set on less than is doing this. Comparing the values of two registers and setting a register or not setting it. Here is a good question. Set on less than is what type of instruction? Well, R type. I need to provide 3 instructions. Set on less than is a R type instruction. I need 3 registers to talk about. Continue talking about inequality. Oh, I think we already talked about this, right? Set on less than, we talked about that. After, if it is set based on whether it is set or not, you can have a branch instruction. Usually combine it with a branch instruction so that after you compare, you can either branch here or don't branch. Over here, what are we doing? If we are comparing T0 to a 0, and if it doesn't equal to 0, then you jump to L1. I shouldn't say jump to L1. I should say that you will branch to an address that is computed using L1. L1 is in bytes. L1 is in words. I'm not spending too much time on the set on less than, branch when not equal, because your eyes are saying, I understand this, move on. Don't do this to me on Monday morning. All right, case or switch. Another useful way of programming things in C, and we could also translate that to Mips code as well. Where is this useful? Well, in a scenario where you have multiple snippets of code to be executed depending on a variety of instruction, a variety of conditions being satisfied. So for example, you can say k equals 0, then we will talk about executing task 0. If k equals 1, then we will talk about executing task 2 and so on, right? So condition, task 0, task 1, task 2, task 3, and so on. So how are you going to do this? We will do build a jump table array, k0 address, k1 address, and so on. What is that address for? It is address, the starting address for task 0, task 1, task 2, and so on. Accomplished using the switch, case switch statements in C. So what are you doing here? You're simply jumping, right? And you're simply jumping using the jump instruction, write code that puts target address in T0. So you're jumping register, right? JR. Jump register is what you're using. So if a specific condition satisfies, then you will do jump register T0, jump register T1, jump register T2, and so on. Those registers are going to have the starting address to those specific tasks. So if you look at jump register T0, what it does is simply jumps to, so it'll update the program counter with whatever is in the T0 register. So first you're going to have to put that target register in T0 and then execute that jump register statement. All right, this is a quick summary of the instructions and followed by their meaning on the right. So it's a summary. Let's not spend too much time talking about the summary. What I'll do is I'll take a minute and see if you guys have any questions. Maybe enjoy my coffee for a bit, and then we can move to the next lecture. What is the time? 9:13. All right, yeah, we can get started with the next one. So here, questions. Okay, looks like you guys don't have any question whatsoever. Next lecture is going to be a continuation of our Mips instruction set architecture. This is the second one. After this, we'll start talking about how do you represent numbers, IEEE 32-bit format, IEEE 64-bit format, the IEEE 754 standards that our computers actually use. So we'll talk about that in the next lecture. Today, we are going to continue with this. Highlights from last time. Well, last time just ended just this time, so we don't need to do the highlights. We can just move on to our lecture here. So C code is an example. And then I'll try to sort of poll the class about what type of instruction or which instruction are you guys going to use to execute a specific C command. So at the top over here, we have a for loop, right? So j equals 0, then you are going into a for loop where you start I at 1, you keep incrementing I by 1 in each iteration, and you go up to I equals 11, right? So you're going from 1 to 11. 11 times you're executing that accumulation, right? Because you're accumulating the value of j in j. J equals j plus I. probably one of your first C things that you learn, right? Writing that for loop. How are you going to translate that to MIPS? Well, there is going to be a step in the middle that is going to help you make that jump, which is to go from C to sort of a pseudocode. What are we doing over here? We are simply writing those instructions more or less in C, but following no particular syntax. I have reserved a column here for addresses. And I'm not writing the addresses in terms of bits, I'm just writing the addresses in terms of their labels, loop and end. So what I'm going to do is talk about whether this translates to this correctly or not, followed by, for these guys, how are we going to write their assembly language? So j equals 0. Well, that is sort of pretty easy to look at, right? Next, I equals 1. Why did we do this? Because we wanted to initialize I at 1. Then we go into a loop. Why do we need that loop label? Because we are going to jump to loop over here. So this is sort of our for loop. You are using if statement to compare whether I equals 11 or not. And if it is, you are going to jump to end. If I equals 11, you come out of this loop and jump to end. Is there a particular syntax for pseudocode? No, it's not. You're just writing things the way it makes sense. Syntax there for MIPS, syntax there for C, no syntax for things that are in the middle. This is something that is helping you make that jump. Now, inside the loop, what are you doing? J equals J plus I, doing that same exact accumulation. You're also incrementing I by 1. So I equals I plus 1. The only thing left is to jump. Jump, compare, accumulate. Jump, compare, accumulate. Until I equals 11, and then you come out of that particular loop. You guys okay with the translation of that for loop to this? Let's talk about which MIPS instruction are you going to use. Don't need to go into detail. We can just talk about the mnemonic of the instruction, the name of the instruction. For j equals 0, what are you going to do? What is that? Add I. Excellent. I equals 1. Huh? No, I equals 1. Which instruction? Same add I? All right. If I equals 11, jump to end. Which one? Branch. So I could use branch when equal. I could also sort of use branch when not equal. It's up to my choice, but I'm using branching statements over there. Next, j equals j plus I. Add. I equals I plus 1. Add I. Jump to loop. Jump, right? Jump address, like jump register, no. Jump and link, no. Just jump register. And then after end, what do you get? You get some instructions, right? Next part of program. Doesn't matter, whatever it is. So at least we are in agreement that those are the instructions that we are going to use. Add I, add, branch when equal or not equal. Let's fill in all the blanks here. So we have used add I for the initialization. We have also included a temp register, a temp variable here to monitor 11 so that we can compare things based on 11. Add I S0 $0 0. That is like saying j equals 0, assuming that we are using $S1 for j. S1 for I, initialize that to 1. Temp T0, initialize that to 11. You see how we are using $0, the 0 register, and add immediate instruction to do this initialization. And it's going to be pretty cool, pretty fast. Why? No memory involved. Doing that in the register file. Then we get into the loop. In loop, we look at whether it compares or not. Branch when equal. Comparing what to what? T0 to S1. T0 has temp, S1 has I. You are comparing I and temp. If it is equal, you jump to end, come out. If it is not equal, you are going to execute these two instructions. One is add S0, S0, S1. The other is increment I by 1. So add I, S1, S1, S1. And then jump loop. So come back. Compare, accumulate, jump. Something similar to what we did just before. Questions here? C program to pseudocode to Mips. And then, once you have Mips, you also have machine language. Good. How do you actually set the what? For the loop. So loop over there is an address, right? You're not going to know the address until you actually have an address space that has been defined. So you define the address space, 32-bit address here, contents, 32-bit address, contents, 32-bit address here, contents, and so on. Once you know that, then loop is how many bits? In that jump instruction, how many bits is the loop? 26, right? Where am I going to get that 4 from? Where am I going to get that 2 from? Those 2 are zeros. The first 4 are the first 4 bits of where that instruction is, right? So that instruction, jump loop, is going to be present at a 32-bit address. Take the first 4 from here, and that 4 will be the first 4 to where that will jump to, right? It will match here. The last 2 will be 0. The 26 in the middle will be over here. So those 26 are going to be specified in binary, in bits, as far as the machine language is concerned. But when you're writing it, say, by hand, you are referring to that as a label, loop, end, and so on. Did I? So because we don't have a memory space that has been set up for us, we are referring to them as labels. But we'll also look at some examples where we'll put some arbitrary numbers in there. We'll take a look about that. Next, this is going to be sort of some aspects of this are going to be redundant because I've kind of said that already a few times. This is more about immediates or offsets for I-type instructions. For load word and store word, the offset is a offset address. It is signed and it is in bytes. How many bits am I using for this? 16-bit offset, right? Which means that I have a range of negative 2 raised to 15, yeah, to positive 2 raised to 15 minus 1 bytes, right? Relative to the current program counter. Relative to the current, sorry, not relative to the current program. It is relative to the base address in the instruction. I'm providing that as a part of the instruction, right? S2 or whatever that register is, which is holding the base address. Those many bytes offset relative to that base address. For load word and store word, it is in bytes. Why is it in bytes? Why is this in bytes and why is the branch instruction in words, which is sort of our next statement, right? For branch when equal and branch when not equal, the offset is in words. Go ahead.
Sometimes you want to assume piece together some parts of different words that might be separated in memory. If you want to load a word.
Right. So whenever can I say this? my MIPS ISA is byte addressable but word aligned. So I can do word aligned branching, but it has to be byte addressable. So I need to be whenever I'm doing that loading or storing, I am addressing things using a target address. So that has to be consistent with the way I've defined my assay, byte addressable. So those are in bytes. Next, BNE and BEQ, those are signed again. I can go up and above PC or below PC, program counter in words. So if those are in words, then it is going to be sort of the same range relative to PC. So you can do PC minus this and PC plus this, but that is going to apply for words. And I can convert that, I can translate that words to bytes by a multiple of 4. So when I do that, my range for branching relative to the current program counter is going to be PC minus 2 raised to 17 in words, in bytes, to PC plus 2 raised to 17 minus 4. So if I'm here, I can go here or here. That range is going to be defined by the offset that I give using 16 bits. For add I and subtract I and for and immediate or immediate, all these immediate type of instructions, my immediate constant is also signed, 16-bit signed number. I have seen a lot of people forget that branching has words and load word and store word are sort of in bytes. Immediate constants. We have already established that this add I instruction is very, very useful in terms of initializing things. Turns out that a lot of operations involve these sort of add I instructions. And because these are making up a large portion of your program, make the common case fast, right? We are going to have small constants, and because they are used frequently, we are going to have a particular instruction for that. The same reason why we did not use add for that. We just had another instruction for it, add I. So add I, subtract I. Design principle, make the common case fast. For small constants, it's going to work pretty well. What are we going to do for large constants? We are going to have to do some manipulations for large constants. And we'll talk about that in just a minute. Let's see. Put small constants directly as operands. 5, 1, negative 18. Signed 16-bit constants. Part of the instruction. Don't have to look into memory. Don't have to look anywhere. Just it's part of the instruction itself. So how does that information get relayed to the ALU? So that 5, that 1, that negative 18 needs to reach the ALU, right? From the instruction register. So who's going to take care of that? So you see this instruction fetch happens. Instruction is ready in the instruction register. Control unit is going to look at the instruction register, decode the instruction, provide the respective opcode for the ALU, along with providing this immediate to the ALU. It is not going to go from the memory. It's not going to go from the IR. It is going to go from the IR through the FSM to the control unit to the ALU. So you're not using the load path or store path as you would for a load or a store word instruction. Let's see. For common constants, you're using 0. That's sort of the same thing as saying when you are initializing some variables, you use, so A equals A plus 5. How are you doing that? Take A, take 0, take 5. Add them, put the result back in A. So you're using that 0 register because that value is going to be constant. Some examples. Add I. This is sort of useful for incrementing the stack pointer by 4. Whenever you push things on top of the stack or remove things on top of the stack, you subtract 4 or add 4 to the stack pointer. So this is very useful for that. $29 is for the stack pointer. So the address of the top of the stack. You guys know stack relatively. I ran out of space in my registers. I'm going to use some part of the memory to do that additional storage. And then we'll talk more about stacks. Let's see. Add I is right there. And this is sort of incrementing the stack pointer by 4. So this is sort of doing this. And I. And immediate. So arithmetic as well as logical operations that fall in this immediate category. This is take the current stack pointer and it bit by bit, bitwise and with 6 and store the result back in the stack pointer. So when you say bit by bit, you know that number of bits have to be consistent, right? When you say bit by bit, 32 can correspond to 32. Over here, stack pointer is 32 bits. Immediate is 16 bits. So where is it going to go? Up or down? Up 16 or down 16? For and I, for or I, for all of these instructions, it is going to be the lower 16 bits. The upper 16 bits for and are going to be what? Oh, these are logical. I don't need to do sign extended. These are logical. So for and I, for or I, if it is going to be the last 16 bits, what are going to be the first 16 bits? They're all going to be zeros in the case of or. They're all going to be ones in the case of and. Let me just verify what I just said. I'm pretty confident about or. Just need to verify about and immediate. Where is it? Zero extended immediate. So it's and is also zero extension. For or, I said zero extension, right? Yes, or immediate, zero extension. So it turns out for and as well as for or, you're padding the most 16 bits with zeros. Oh, wait a second. All right. So, and I, immediate and. Take S2, 32-bit, bitwise and with 6, right? So 6 is right there, and you have a bunch of zeros over there. Bit by bit and store the result in S1. This sort of and immediate and or immediate are sort of useful to help work with large constants. And we'll take a look at an example in just a bit. And we are going to do the similar thing for or immediate. ITAP instruction, you have 16-bit constant over here, 5 bits for source, 5 bits for another source register, and 6 bits for the opcode. Go ahead.
I forget the word for this sort of like phenomena, I guess, but when you're comparing these, when you're comparing an and I or bit by bit, will the instruction stop as soon as it reads like a false, or will it continue through the?
But we are not comparing, right? So we are doing the operation. So for add I, doing like workhorse, no comparison. Actually doing the add, actually doing the and. So, but if your question is about comparators, there are 2 types of comparators. One, the moment things break, you come out. That the other type of comparators. So it depends on the design of the comparator. They keep going until the actual final result is computed. So if you're doing a cascading of smaller size comparators to make bigger size comparators, then it is possible to stop immediately the moment it breaks. Right. So it depends, cascading versus not cascading. It depends on that. Right. Oh, no. So I was talking in terms of strictly comparing things. So if you are comparing, say, two numbers, right? You will start with the most significant bit, right? You guys remember this from Coco? You start with the most significant bit and then you work your way down to the least significant positions. When you start with the most significant, the moment it breaks, technically you should just break, right? Like it's not equal. And that is possible if you are sort of designing your comparator in a cascaded form. If this happens, then do this, and then provide an output, provide an output, provide an output. But if you are making a 4-bit comparator that is sort of having 4 bits here, 4 bits here, circuit, 3 answers, equal, greater than, less than, then in that case, you just have to wait for it to get computed all the way down. So then you cannot stop even if it breaks right away. So that depends on the design of the comparator. All right, come back to this. Large constants. 16-bit constant, fine, use immediate instructions. What about large constants? For example, 32-bit constant into a register. How do you load a 32-bit constant into a register? Load word instruction has, it doesn't allow us to do a constant, right? I cannot move a 32-bit constant into a register. How do I do that? Well, you can do this. 2 instructions. The first one is a load upper immediate. Load upper immediate is a high type instruction in which you are loading this particular constant, 16-bit constant, into a T0 register. Load upper immediate, register followed by the constant. I type instruction, load upper immediate. So once you do this, what do you have? The register will do this, right? 16 bits are loaded from the constant, a bunch of zeros on the other end, on the load 16 bits. Second instruction is OR immediate. OR immediate what? Take T0, current T0, OR it with these bits, which are load 16 bits, put the answer in T0. So because we are doing a 0 extension here for the constant, you've got this constant over here, 0 extended. Now you do bit by bit OR, you compute a 32-bit result that goes into T0. So these 2 instructions combined, we were able to make a register T0 to a particular constant. So it required 2 instructions. Now here is the thing. If you look at the Mips instruction reference sheet, you will see a load immediate instruction, right? LI. Now here is something that I want you guys to sort of play around with when you have time. Try to use that simulator that we talked about. Execute a load immediate instruction. Look at the assembler, what it does. Your assembler actually takes the LI instruction and executes in the background LUI and OR immediate. So it actually takes in the load immediate instruction and actually executes load upper immediate and ORI. So it actually does this. The user doesn't know it because the assembler is taking care of that in the background. But that's what it is doing. Let's see. But you will see load immediate over here. Load immediate somewhere here. It will be here. LI. We have load upper immediate. Is there a load LI here somewhere? Probably not. Okay, so it's part of a bigger instruction set, which is not available over here. But that is a thing in MIPS 32, load immediate. If you did that, the assembler would execute these 2 instructions. Let's see, questions here? So these are sort of the questions that you guys should be answering. Why was loading a 32-bit constant into a register not possible without these 2? Right? Could I have done it with just 1 instruction? If not, so how much could I have done? Could I have done 16-bit? Yes, 16-bit I could have done using add I or whatever. That was a small constant. For large constants, I couldn't do it beyond 16 bits. So I used this 2 instructions, load upper immediate and then or immediate to tackle the upper 16 and then the lower 16. Is this the only way to do it? There are other ways of doing it. This say manipulation of upper 16 bits and lower 16 bits, you could do it in other ways as well. Doesn't have to be this. What is the time? 9:41. All right. So this is what happens to me usually. Whenever I talk about stacks in procedure calls, students tend to forget that we talked about stack pointers and stacks and procedure calls. So I'm going to start this Thursday morning, 8 a.m. when everybody is fresh, so that you guys know we talked about this for sure. So I'll stop over here. We'll pick it up with stack pointers when we come back on Thursday. Let's stop recording here. I think I can stop recording here.